So our last speaker for tonight is Sven Hallberg, and he's going to talk about Zcash, anonymous cryptocurrency. The subtitle of this talk is Zero Knowledge, Succinct, Non-Interactive Arguments of Knowledge for Lay People. If there are lay people who could memorize that and can repeat, you get karma points. Sven is a mathematician, a coder, a cryptographer. He also does functional programming in C, which probably makes him the person you might want to listen to. Please, a round of applause for Sven.
Thank you. Thanks for the introduction. Thank you all for coming. So the short version of the subtitle is ZK snarks for the interested layperson. Quick check, has anybody from the audience heard the term ZK snark before? Oh, that's more than I expected. Okay. So at the end of this talk, hopefully you will know how these things can be used to build a cryptocurrency which is kind of like Bitcoin, but has better privacy and anonymity properties. Little disclaimer, I won't be able to explain to you how the ZK snarks work. So please don't be too disappointed by that. That will be another talk for next year, maybe. All right, so let's start right. Zcash is, like I said, it's a cryptocurrency, magic internet money. Kind of like Bitcoin is in fact based on the Bitcoin code base, so it's kind of like an altcoin that you may know. But other than a lot of other coins, it actually adds a substantial new feature to the protocol. And that is mainly a new type of transaction that is capable of shielding the sender, the receiver, and the amount of money being transferred. Now this type of transaction lives next to the regular Bitcoin type transaction, so you actually have two types of addresses. One that's called a transparent address, starts with a T, and a new type of address that starts with a Z or Z, which gets used by the new type of transactions. And yes, like I already said, it uses these so-called ZK snarks, which are relatively recent kind of mathematical magic, as I like to say. I think the earliest, 2010 is the earliest citation from the Zcash spec. For a little bit of history, Zcash is an evolution basically of two academic proposals, one called Zero Coin, which was still pretty different from Zcash, and the other is called Zero Cash, and that is already almost like Zcash. So you could consider Zcash an implementation of Zero Cash with some refinements and improvements. Now, a number of the inventors of Zero Cash and a number of other people have formed a company in order to actually get the system off the ground as its own altcoin. And I'm told they are also in the process of forming a non-profit foundation to govern the future development or something. Little disclaimer, I am not affiliated with any of these entities. I'm just an interested bystander who happens to think he can explain this stuff a little bit. Because we don't have so much time, this talk is going to focus entirely on the technical aspect. There are also other interesting questions, but I just want to explain how does this system work in the abstract, what do the transactions look like, what exactly is being hidden, what isn't hidden maybe, and how can you verify even the validity of a transaction if you know almost nothing about it. And lastly, it'll then become clear where the ZK snarks come in. So if you know Bitcoin, this is, just to recap, this is a Bitcoin transaction. sorry. So imagine Bitcoin. I don't want to go into blockchain or any of that here because we don't need to. Please imagine Bitcoin just as a long list of transactions that is publicly verified. That is entirely enough for this talk. Because the Bitcoin system is basically transferred over for the transparent world, we can just focus on an individual transaction, okay? So this is one single Bitcoin transaction of which you have a long list in the world. And each such transaction takes a number of input amounts from previous transactions and then declares a number of output amounts to some receiver addresses. And in order for this transaction to be valid, you need most of all, well, these two things, you need to show that you actually have authority to spend the inputs, and you need to make sure that, well, the input amounts balance with the output amounts, right? Now, like I've already alluded to with Zcash, the picture looks almost exactly the same, except there's a new block at the end of the transaction that adds some things called join splits. And yeah, what these are and how you can verify and prove their validity is the main topic. So let's jump right in. What does a join split look like? So as a major difference from Bitcoin, value in these new Zcash transactions is actually transferred in the form of virtual coins. Right? That's kind of ironic because Bitcoin, despite the name, doesn't actually contain any sort of coin concept anywhere. Here we have that. And you can see from the picture that each join split takes 2 coins as inputs and it generates 2 coins as outputs. So the input coins are consumed and no longer valid at the end, and 2 new coins come into existence. So why 2? Just really quickly, that's because that is general enough for anything. If you just want to consume 1 coin, you set the other to 0. If you just want to produce 1, you set the other to 0. And if you want to consume more or create more, you just combine multiple of these join splits in the same transaction. Okay. And now the important part, each such virtual coin has a, well, what's called a plain text that is basically a tuple of values that contains the information about that coin, namely its owner, its value, and some technical values that we'll get back to. And this stuff is kept secret. It is known by the owner of the coin, but nobody else. The only things that are published, actually, in the blockchain, as part of the join split statement, are these so-called nullifiers on the left here and commitments on the right. Don't worry so much about what those are for the moment, but these are just numbers that are uniquely derived from the coin plain text. And yeah, the nullifiers are always used when spending the coin, and the commitments are always used to bring the coin into existence. So since these numbers are different, and they are actually derived in such a way that they cannot be matched to each other, you can't immediately trace a transaction, right? This is called a nullifier simply because it is a value that essentially nullifies the coin, right? It gets consumed. After that, it is no longer a valid coin. And the way this works is really simple. I can explain this on this picture. Each node in the network simply keeps a list of all the nullifiers it has ever seen, and it keeps a list of all the commitments it has ever seen. And when a new join split comes in, it simply checks the nullifiers against the list it has already seen, and only if it is nowhere in there, this is a coin that's still valid. So that's really simple. This is double spending protection, very important, obviously, but that doesn't require any magic yet. What requires magic is, well, checking that I don't pull these numbers out of thin air, that they actually correspond to actual coins and that everything balances out. The values need to balance, I actually need to be the owner of the coins, and so on. And explaining how that works is the rest of the talk. So this is what the join split looks like in less of a picturesque form, more of a formal form. This is actually from the paper with slight adaptations for readability. You can see there are a number of values. We're not interested in most of them, but you can see the two nullifiers here for the input coins, and you see the commitments for the output coins, and then you see a value called RT. That is a number that uniquely identifies the set of commitments in existence at that moment. So it establishes the context for the nullifiers, for instance. If you know what a Merkle tree is, this is actually the root of a Merkle hash tree. If you don't know what a Merkle tree is, don't worry. Simply think of it as like I said, a number that uniquely identifies the set of coins in existence. And then, lastly, the interesting and most important part, way at the end here, that little pi, is a so-called proof of validity. And that is just a simple number that somehow, with some process, is supposed to convince us that this transaction is valid and conforms to all the things all the conditions we expect from a valid transaction. And to kind of motivate how that could work, without going into too much detail right now, imagine if I could convince somebody that I simply know the note plain texts for 4 notes, the 2 input notes and the 2 output notes. If I can convince somebody that I have these plain texts and that these 2 nullifier values do correspond to the 2 input coins, and these 2 commitments do correspond to the 2 output coins, and the values balance out, and the 2 input coins actually exist in this Merkle tree here, then this is already intuitively, this is convincing of some sort. And that is basically the game plan for us. And to make that more precise will be our job. Now, really quickly, the titular Zk snarks. It's already been introduced. What it stands for is a zero knowledge, succinct, non-interactive argument of knowledge. So this is this black box lets us do what I just alluded to. Perform that proof that we know these note plain texts and that they also satisfy our requirements. And this is the abstract API, really simplified, of a Zk snark system. Maybe a little caveat, there are multiple constructions of Zk snarks, not a single one. But so we're talking about the one that is used in Zcash. So at first there is a one-time setup procedure. This is, by the way, a concept of some interest, but we also don't have time for that one. This was actually done a week prior to the launch of Zcash, this setup procedure, and it's a very interesting story. If you want to read it, there are several people involved in there, and they have written accounts on how it all went. So that's really interesting, but we have to skip it, unfortunately. And then we have this proof procedure that we give some inputs, in our case, the note plaintexts, and it generates this little pi value that we can put into the verify procedure, notably without the input. And if that returns true, we should be convinced that the prover knows this input such that it satisfies the statement that we set the whole thing up for. And that you just put into libsnark. It is literally on GitHub, and your system works. hopefully. All right. So to make this all concrete, the so-called joint split statement, this is the collection of conditions for validity of a transaction. So it is basically what I already said. The prover knows 4 notes that satisfy these things. Each note consists of 4 values. That is the address of the owner, the value of the note, a pseudo-random number called rho, another random number called r. These are of technical interest. We'll kind of gloss over that. And these should satisfy the statement that the input notes appear somewhere in our Merkle tree of existing notes. The nullifiers correspond to the inputs, the commitments correspond to the outputs, the values balance, and we also have spend authority for the inputs. And then non-malleability and uniqueness of rho are more technical. Non-malleability means that this joint split, this proof is uniquely tied to this particular joint split, and uniqueness of rho is similar for the pseudo-random number that has to be actually pseudo-random. All right, so, sorry, let's go back for 1 second. How do we encode this in a form that the ZK-SNARK system can actually make sense of it? So if there are any programmers in the audience, you know how to encode lots of things in some sorts of code. And this picture on the next slide should probably look familiar to many. This is a Boolean logic or a circuit diagram of a Boolean circuit that computes some logical function. This is just a stupid toy example, of course. That takes some inputs on the left, and then these Boolean values run along these wires, are combined by these gates here, and you get some output value to the right. Now, you know, this is enough to do all the things in your computer. So this could be intuitive as a way of encoding things. However, it turns out Booleans are mathematically not that nice because everything immediately collapses to 0 or 1. So what the ZK-SNARKs and Zcash actually use is a variant called an arithmetic circuit, where the values along the wires are actual full-blown numbers, and the gates perform the arithmetic basic operations of addition or multiplication. So this is another toy example as a circuit for adding 2 numbers and squaring them and then multiplying by a third number. And as it turns out, we can use these arithmetic circuits also to represent Boolean operations. This is multiplication. And if you consider the inputs restricted simply to the set of values 0 or 1, the output is also 0 or 1, and it is 1 if and only if both inputs are 1. So that's Boolean AND. Here's Boolean NOT. That's the function 1 minus x. That is 0 if x is 1, and it's 1 if x is 0. So we can do a lot with these circuits. We can encode all kinds of, expressions or functions in them. But what we have in our joint split statement are actually conditions, right? Things like this value has to equal that value or the sum of that value or so. So how do we get there? And for that, we need to introduce the concept of satisfiability. Again, this arithmetic circuit, we call it satisfiable if we can find an assignment for the input values here such that the output becomes 0. Why 0? Because that immediately leads us to satisfiability of equations. So consider maybe this equation at the top here. If we want to know whether this is satisfiable by some assignment to x, y, and z, well, do your high school math. Instead of talking about equality, talk about the 2 sides being equal, talk about the difference between the 2 sides being 0. So just transform it like this, build an arithmetic circuit to represent the left side, and then talk about satisfiability of that circuit so that this left-hand side becomes 0, and then you know that these values satisfy that equation. And ZK-SNARKs not just allow you to prove, well, satisfiability itself, and that is existence of any assignment that satisfies it, but it allows us to prove knowledge of the actual assignment, right? So our node plaintexts. So this is kind of our game plan. You probably have a picture now. Our plan is to encode the join split statement that you've seen in formal equations and such, then turn all those into an arithmetic circuit, plug that into our libsnark, and use it to prove knowledge of the nodes such that the circuit is satisfied. Now, if we want to think back, what is it actually that we have to encode in the join split? What are the ingredients? I said something about a hash tree, these commitments involved, and I mentioned a pseudo-random function. Finally, for the balance, we need regular arithmetic. So the first three of these are actually all instantiated with a hash function that you know, SHA-256. So we basically just need to build an arithmetic circuit for SHA-256, and then the rest is variations of that. SHA-256, if you've ever seen a description of it, contains lots of binary operations or arithmetic on binary numbers. And so the Zcash implementation, or zero cache, actually chooses the route of representing all of the numbers natively as binary. So if you have, say, a 32-bit number, you take 32 wires, each of them carrying only a 0 or a 1, and only if you need the actual direct representation, let's say for your balance arithmetic, you convert that with an arithmetic circuit that simply computes the value of the binary representation with the regular formula there. And you can also go back with a little trick that I don't want to get into, so as not to confuse. And you can also do a thing like, well, bit shifting or other permutations of the bits simply by, well, permuting the wiring in the correct way. So this will be a bit shift by 2, right? You get the values in at the bottom, and then, yeah, reroute everything 2 places to the right. And so this should already give you a good idea of what to do, right? You just need to look up SHA-256, take all the pieces, transform them all into these arithmetic circuits, just combine everything together. And when you're done, it looks something like this. So this is from the Zero Cache paper. They have this wonderful salad in there, which is basically just, boil it all down. So the H here, that's SHA-256. You see that a lot, but actually not that much more. There's concatenation, right? This bar. There are some constants, and there's regular arithmetic numbers. So this down here is the balancing. And some values plus some other values have to equal some values. Here's a check for overflow. That's also easy to represent if you think about it. Here is the condition that the commitments are formed correctly. Here's the nullifier being formed correctly. The only thing that's missing from this picture is the Merkle tree lookup, because that didn't fit on a single line, so they don't have it in the paper. Too bad. Yeah, but that's basically it. So I think we have like 7 minutes for questions.
We'll do a short Q&A right now. Please come up to the microphones. Number 4.
Assuming that there is a bug and that someone can create money out of thin air using this anonymous, is there a way that the community can at some point see that there is much more Zcoin than
there should be?
Yeah.
So Not immediately, and this is actually one of the big dangers. So it's a very good question. One thing that you can see, if you remember the slide with the join split statement, you can see when coins are created and you can see when they are spent. So at any time, the system has a picture of how many coins have been created so far and how many coins have already been spent. But it's not, that of course doesn't give you exactly what you want. And there has actually been talk about extending the system in the future to include a sort of regular account where every node is required to regularly transfer all their money into the transparent world, and then at their leisure transfer them back. So it wouldn't actually hurt your anonymity, but that's not in there yet.
Thank you.
Okay. One question from the internet.
Is a split of the chain in Zcash possible?
A fork, you mean? Yes. That would work exactly as in Bitcoin. So yeah, all the conditions and everything are enforced by the same sort of consensus mechanism as in Bitcoin.
And the last one, microphone number 8.
Yes. I was wondering if you've kind of looked at the funding aspect and the ethical aspect and the algorithm of Zcash, and I was wondering what you think about those, because when I looked at how they're funded and what the algorithm, how the algorithm is collecting money for the developers and for the investors, I found that in the first 4 years, 20% of all the coins will go to the developers and the investors, and after that it stops, and the total amount that will ever be made of coins, 10% of those will then be for the developers and the investors. What do you think ethically about the choice they make there? Because they are kind of algorithmically programming the inequality there.
Well, okay. So I can, of course, only speak from my own interpretation of this, and I will admit I didn't look at it too closely because I was mostly interested in the technical side, but the way I interpret it is that I think they did this did this way, that in order to have an alternative that's better than a pre-mine. I think they didn't want to do the pre-mining thing that some currencies do, where the initial developers just generate a bunch of coins that then they own, and they also have this slow start mining, which I couldn't mention. That means that the first few blocks, I don't know how many, the mining reward is lower and it slowly ramps up. And I think they did those things in order to avoid a situation where the developers have a lot of power concentrated in the beginning. And I think this founder's reward that you mentioned, where it is put into the algorithm that for the first 4 years they get a percentage of all the mined coins, is basically to just balance that out, to do that in a fashion that's transparent. I think that's the intention. Apart from that, you said about basically algorithmically making this choice. So how do I interpret that ethically? I would say, well, it is put by them into the algorithm, but it's still the network consensus that confirms it. So there's absolutely nothing stopping the network to democratically decide we want only half the share for the founders or no share at all. And there's basically an alternative Zcash. I don't know if it took off or not. That just simply rips out the founders' reward. And there's also another one that simply that replaces it with something else entirely. So there's a big discussion to be had about that, and I think it's pretty interesting. But that's basically my interpretation.
Thank you.
One more question, Mike 7.
Yes, you already went into this a little bit, but I wonder what alternative zero cash solutions you have looked into? Because, for example, there exists Monero, which is based on a different hashing algorithm, I guess, but I don't really know the differences.
Yeah. I have to admit I am not familiar with Monero. I know only that Monero uses something called ring signatures, so there is some math magic in there as well, but I haven't looked at the differences to that. I'm guessing that the privacy guarantees that they can make are less strong than the ones in Zcash, but I don't know the details.
And this is it for tonight. Please, a round of applause for our last talk.